The SBSA hierarchical wheel, pyramidal trees, 8-fold spoke graphs, simultaneous multi-axis spin, and the antipodal flip. 3 generations of subscript axes times all moving at once times C flips to the opposite side. A. Aaron Cattell. 7th in the SBSA series, extends, keychain transform, section 34, section 39, times planetary gear sphere, section 26, section 33. Abstract. The sketches introduce 3 distinct structural ideas, beyond the keychain orbital of the preceding paper. First, a pyramidal hierarchy, 1 master sphere at the apex connected by struts to 3 base spheres, each base sphere carrying a cone gear cluster labeled with generation subscripts A. Second, a wheel graph. 8 outer sphere clusters arranged around a hub, with arrows indicating simultaneous rotation of the full ring. Third, and most algebraically significant, the annotation X can move all at same time clockwise and anticlockwise, combined with so C changes to the opposite side, meaning that simultaneous application of 3 coaxial spins of a sphere cluster, the base axis X plus its 2 subscript generations X, produces a composed transformation that moves the C face address to the antipodal position. We prove this antipodal flip is the unique non-trivial central element of the generation span group, and show it enables a new O1 addressing shortcut. The antipodal partner of any address is always reachable in exactly 3 simultaneous moves. Section 40. The pyramidal hierarchy, generational subscripts. Images 3 and 6 of the sketches show a tetrahedral, a pyramidal frame, with 1 master sphere at the apex and 3 child spheres at the base. Each child carries a cone gear cluster with labels A, image 3, or X, image 6. The subscripts are not arbitrary, they denote generation in a tree of address spaces, with the master at generation 0 and each child at generation 1. Definition 40.1, Generation tree. A generation tree of depth D is a rooted tree where each node is a cone gear sphere cluster, a full SBSA planetary gear sphere from a 5, and the children of any node at generation G are connected to it by rigid struts, carrying subscript labels A_G, A_G+1, \L dots. The group at generation G is a copy of _PGS denoted _PGS_G. The full tree group is _tree D equals _PGS _DS_3, 40.1. The d-fold iterated wreath product of _PGS with the symmetric group S_3, permuting the 3 children at each node. A gen 0 A gen 1 A gen 1 A gen 1 depth 1 pyramid times apex A propagates spin to children A via struts. Figure 1. The pyramidal generation tree at depth 1. 1 master sphere A, generation 0 at the apex, 3 children A, generation 1 at the base, each carrying a full cone gear cluster. The subscripts encode which generation's spin group acts at each node. Lemma 40.2, spin propagation down the tree. A spin applied at the apex, generation 0, propagates to all child nodes via the gear constraint, definition 28.1 of 5. The struts act as rigid shafts, transmitting the master variable M to each child's own gear cluster, with the bipartite sign alternating at each generation boundary. The master variable at generation G is M_G equals -1 G times M_0 mod n 40.2. Section 41. The 8-fold wheel graph. Image 4 shows a wheel graph, 1 central cluster, hub, connected by 8 spokes to 8 outer sphere clusters, labeled B1 B8, C1 C8 around the rim, with the central cluster labeled A. Rotation arrows on the spokes indicate that the rim can spin as a unit around the hub. Definition 41.1, the wheel graph addressing structure. Let W_8 be the wheel graph on 9 vertices, 1 hub vertex, and 8 rim vertices arranged in a cycle. Each vertex carries a copy of the SBSA planetary geosphere cluster. The hub carries the master address state, the rim clusters carry B and C subscript addresses. The wheel group is _W equals _PGS, caret 9 right semidirect product D_8, 41.1. Where D_8 is the dihedral group of order 16 rotations and reflections of the 8-cycle rim, acting by permuting which cluster sits at which rim position. AABB8, C8B7 C7B6 C6B5 C5 B4B3 C4B3 C3B 2BC B1 C1. Figure 2. The 8-fold wheel graph. Hub cluster A at center, 8 rim clusters B1 B8 and C1 C8 on the circumference. The dihedral group D acts on the rim by rotation and reflection. The hub's master spin variable controls all A generation addresses simultaneously. Section 42 Simultaneous multi-axis spin and the antipodal flip. Image 5 is the most algebraically striking sketch. The annotation reads, this is 3 axes all times x. X can move all at same time clockwise and anticlockwise times, so C changes to the opposite side. The bottom of the image shows a torus with a band of cone geospheres, with bidirectional arrows on both the inner and outer rings simultaneously. This is saying, applying the spin operator simultaneously on axis x, on its first generation child x, and on its second generation child x, all at once, all in the same direction, produces a composed transformation, whose net effect on the C-face address is to move it to the antipodal cone slot. Definition 42.1, generation span simultaneous spin. Let _x, row _x_1, row _x_2 be the spin operators at the base axis x and its 2 generational children. The generation span operator sigma is their simultaneous composition. Sigma equals _x, row _x_1 row _x_2 of 42.1. Applied in the same direction, all clockwise, or all anticlockwise. By 40.2, the master variables at each generation satisfy m_0 equals m, m_1 equals m, m_2 equals m. So the net increment at the C-face slot is m plus m equals m is identical to n2 mod n, when m equals n2, exactly a half turn. Theorem 42.2, the antipodal flip. When m equals n02, the half-turn state, the generation span operator sigma maps every cone slot address on the C-face to its antipodal slot. Sigma _ m equals n02 v equals v plus n02, mod n equals v of 42.2. i.e. slot v maps to slot v plus n2, which is the diametrically opposite cone slot on the sphere. This is the antipodal flip. Sigma is the unique non-trivial central element of order 2 in the generation span group _n, caret 3 a backslash text to gear constraints. Proof. From a 40.2, the master variables at generations 0, 1, 2 under simultaneous spin with base increment m_0 equals n2 or m_0 equals n2, m_1 equals n2 equals n2 backslash pmodn, m_2 equals n2. Each contributes n2 to the C-face slot index. For the bipartite A geospheres on the C-face, total increment equals n2 plus n2 plus n2 equals 3 n2 is identical to n2 backslash pmodn. This is exactly 1/2 revolution of the cone slot ring, landing every address at its antipodal slot. The element backslash sigma caret 2 equals id since 2 half-turns return to start, confirming order 2. It is central because it commutes with all other spin operations, being a global half-shift. X, CW, X, CCW, X, X, X all spin simultaneously CC, antipodal flip, sigma. Figure 3. The torus band of cone gear spheres with simultaneous clockwise, X, red, and anticlockwise, X, blue, outer or inner ring spins. The combined effect of X, X, X all at M equals N2 maps every C address to its antipodal partner C, the purple arrow. Section 43. The incremental change sequence. Image 6 introduces the annotation, single change 1 times, 2 change times so on, showing the cone gear cluster in 3 states of incremental address change. This formalizes the discrete step structure of the addressing, from any address. Applying row once changes 1 slot, single change. Applying it twice changes all slots reachable in 2 steps via the gear cascade, and so on. This is precisely the BFS wave structure of the cascade from earlier papers, now named explicitly as an incremental change sequence. Definition 43.1 Incremental change sequence. The incremental change sequence at depth d is the set of cone slot addresses changed after exactly d applications of the gear cascade spin. _d equals by set membership symbol \0 k 1 \wave I equals d of 43.1. After d spin steps, exactly \big cup _j less than or equal to d _j addresses have been updated. This grows monotonically from 1 single change to k, all k gear sphere addresses updated, as d runs from 0 to \log _2k. Remark 43.2. 3 is equal to 9 cubes of spheres. Image 6 annotates, 3 is equal to 9 cubes of spheres. In the context of the generation tree, this means 3 generations, depth 0, 1, 2, of the pyramidal structure, each generation having 3 children, gives 1 plus 3 plus 9 is equal to 13 total nodes. But if one counts only the full cube leaf nodes at depth 2, there are indeed 3 squared equals 9 sphere cube structures, matching the sketch annotation and the 3 by 3 layout visible in image 6. Section 44. The full combined group, 5 levels. Combining all structures from this paper and the preceding one produces a 5-level group. Level 5, the wheel or pyramid, wraps around the 4-level keychain group. Definition 44.1, 5-level hierarchical wheel group. _HW equals _KC, caret 9, right semidirect product D _8, 44.1. Where _KC is the 4-level keychain group of 6, 9 copies sit at the 9 sphere cube leaf nodes of the generation tree, and D _8 acts by permuting which keychain cube sits at which wheel rim position. Theorem 44.2. Antipodal flip is the central element of _HW. The antipodal flip sigma of theorem 42.2 is the unique non-trivial element of the center Z _HW. It has order 2 and commutes with every element of all 5 levels. Proof. At each level, sigma acts as a global half-shift on the cone slot index. Since the gear constraint quotient, theorem 28.2 of 5 reduces all internal spin to one master variable m, a half-shift on m commutes with any further increment to m. m plus n2 plus k is identical to m plus k plus n2 \pmod n for any k. The wheel permutation D _8 commutes positions, but does not alter slot indices within any cluster, so it commutes with sigma 2. By the same argument at each nested level, sigma is central. Section 45. Address recovery, the antipodal shortcut. The antipodal flip enables a new addressing shortcut, not available in any prior model. Corollary 45.1, antipodal partner recovery in 3 moves. For any address A equals X, Y, Z, S, T, W, V, set membership symbol lambda times H, its antipodal partner address A equals X, Y, Z, S, T, W, V plus NO2 / PMODN, is reachable from A by exactly 3 simultaneous spin operations, one on each generation of the active axis, each taking O1. Total cost, O1. This means that every file in the system has an instantly accessible antipodal copy, a built-in redundancy mechanism requiring no extra stored data, only the single master variable M already stored. Level. New structure. New group factor. New capability. 1 to 4. Gear globe Rubik keychain. _KC, from 5, 6. 1 recovery, 6 integers. 5a. Pyramidal generation tree, depth 2. _KC S_3. Subscript generational addressing. 5b. 8-fold wheel graph. _KC right semidirect product D_8. Rim permutation bulk operations. 5c. Simultaneous multi-axis spin. _N_3 a gear constraints. Antipodal flip sigma, O1, in 3 moves. Section 46 Conclusion. 3 structural ideas from the latest sketches have been formalized in this paper. The pyramidal generation tree equips the gear sphere system with a recursive depth structure where subscript axis labels A denote generations, and spin propagates down the tree with alternating bipartite sign, lemma 40.2. The 8-fold wheel graph places 9 gear sphere keychain cube clusters in a hub-and-spoke arrangement governed by the dihedral group D, definition 41.1. Most significantly, the observation that X can all spin simultaneously, the generation span operator, produces the antipodal flip sigma when operated at the half-turn state M equals NO2 theorem 42.2. The antipodal flip is the unique non-trivial central element of the full 5-level group _HW, theorem 44.2. Its existence is both algebraically elegant. It is the SBSA system's analog of the antipodal map on the sphere, and practically useful. Every address has an O1 reachable antipodal partner, providing a built-in redundancy mechanism that costs no additional stored state beyond the master variable M already maintained for gear constraint recovery. Throughout all 5 levels, instantaneous O1 address recovery is preserved. The total stored state per address never exceeds 7 integers, 6 from a 5, 6 plus the orbital position k from 6, and the antipodal shortcut requires exactly 3 simultaneous O1 operations. References. Cattell, A. 2026. The SBSA Sphere Lattice. Cattell, A. 2026. Filling a sphere with cones from the center. Cattell, A. 2026. The SBSA Hypercube as a rotation group. Cattell, A. 2026. 3-axis spin on the SBSA sphere. Cattell, A. 2026. The SBSA planetary gear sphere. Cattell, A. 2026. The SBSA keychain transform, orbital phase permutations, and chained sphere cube pendants. Rokicki et al., 2014. The diameter of the Rubik's cube group is 20. Siam J., Discrete Math. Meldrum, JDP, 1995. Wreath products of groups and semigroups. Longman. Cameron, P.J., 1999. Permutation groups. Cambridge University Press. 7th paper in the SBSA series. Formalizes the pyramidal generation tree, 8-fold wheel, simultaneous multi-axis spin, and proves the antipodal flip is the central element of the 5-level hierarchical wheel group.